Hi, I am Ecem from Middle East Technical University. This session is a part of EXA4MIND training sessions, and today we are going to learn about vector databases. First, I'm going to give a brief introduction to vector database terminology, and then I'm going to show you some search types, some query examples, and then we are going to start coding with Gökhan. So let's start with vector database terminology. Embedding. Embedding is a numerical representation of data. It can be textual or visual data. And with the help of embeddings, we can preserve semantic meaning of our data. You can think embeddings like high-dimensional matrices. And embedding models are tools that enable us to convert our data into these embeddings, these high-dimensional matrices. As you can see, both textual and visual data can be converted into these high-dimensional matrices using an embedding model. And semantic search is searching based on meaning, based on content, not on exact keywords or matches. There are various application areas of semantic search: finding similar images, searching documents by their content or topic, or multilingual search can be said among applications of semantic search. And vector databases are systems that are designed to store, index, and search these vectors efficiently. After embedding your data, it can be image or text, you can store them in vector database and perform your queries on these databases. There are a lot of options for vector database and for embedding models. These are some of the popular ones. You can choose any of them based on your needs, based on your data set. Today in the session, we are going to use Milvus as vector database and Clip as embedding model. We chose Clip because it can convert both text and image data into embeddings. And today we're going to use a Flickr dataset, and it contains both text and images. So Clip was the best option for us. As I said, you can choose the best option based on your needs and your dataset. As I explained, we are going to use a subset of the Flickr dataset. It contains images, and each image has a short text description. Today, we're going to perform three main query types. The first one is single type search. It has two subtypes: image-to-image vector search and text-to-text vector search. And the second one is cross-type search. Again, there's two types: image-to-text vector search and text-to-image vector search. And the last one is hybrid vector search. I'm going to go over them one by one. The first one is image-to-image vector search. This is a single type search. Here, after embedding our query image, we perform a vector search on other image embeddings. We call this a single type because we give image and perform our search on images, or we give text and perform our query on text embeddings. We're working with just one type, so we call them as single type search. Let me show you an example. This is our query document. As you can see, we have an image and we have a short text description. We embedded query image here and performed a vector search on other image embeddings. Here, these are the results. As you can see, these documents are visually similar to our query document. And the second type is text-to-text vector search. Again, this is a subtype of single type search. We are working with just textual data. After embedding query text, we perform vector search on text embeddings, and we retrieve our results based on these scores. Here, as you can see, results have significantly changed. These documents' text descriptions are similar to our query documents text, but here we didn't consider any image data, so they're not that similar to our query documents image. And our second main query type, cross-type search. Here we embed query image and we perform a vector search on text embeddings, or vice versa. We call this cross-type because if we embed image, we perform our query on text, or if we embed text, we perform our query on images. So let me show you results of image to text vector search. As you can see, these text descriptions are closer to our query's image. We didn't consider images of these documents, so they're not that similar, but their texts are closer. And the second subtype is text-to-image vector search. After embedding query text, we performed a vector search on image embeddings. This is a different approach. So results are significantly different here. These documents are not visually similar to our query document's image, but they're consistent with our query document's text description because we didn't consider our query document's image here. You can choose any of these search types based on your needs. So this yielded very different results. Actually, you can combine any of those search types as you want, and you can produce a hybrid vector search. But here in this session, we're going to perform our hybrid search as in this schema. After embedding query image, we perform two different vector search. The first one is among text embeddings, and the second one is among image embeddings. And after getting scores of these vector searches, we summed their scores and re-ranked our documents. Before summing them, you can multiply them with different constants so you can arrange the importance of your text or image search. Here we have an equally weighted hybrid vector search, and these are our results. And then we wanted to increase the importance of image search. So before summing them, we multiplied image search scores with 0.8 and text search scores with 0.2. And then we summed their scores and re-ranked our documents. For this case, results didn't change with equally weighted one, but this may change. This may alter from the data set or query document you use. And in the last one, we wanted to increase the importance of text search. So we multiplied text search score with 0.8 and image search score with 0.2 and then summed them. Here, as you can see, results are very different from the previous one. As I said, you can arrange them based on your needs. You can play with these constants as you want, and you can produce your own hybrid vector search. This is all for introduction part. Now let's start coding with Gökhan.
Thank you, Ecem, for your presentation. Hello, everyone. I'm Gökhan, and I'm going to start with the code parts based on the Ecem's topics. And we have mainly two topics for subtopics for the coding part. First, I'm going to introduce you to the basics of the Mills databases usage. And afterwards, I'm going to show an example for how do we use Mills in a real type project. But first, I want to show you the documentation of the Mills, because first you need to install the Mills. We are using here Mills standalone, and we are using Docker desktop. But if you want, you can visit this documentation site and install with whatever you want. But in the case of for example, if you use Linux, you can use these two sections to learn how to download Mills. We are not covering that in our session. We are just show you how you can use Mills. Except the installation of the Mills, we need a dataset. As Ecem said, we are using Flickr 8K and we have captions. As you can see, we have images, and per image we have 5 captions. But in our session, for simplicity, we are using just first caption and leave the other four. There are various ways, of course, but for simplicity, we are just using the first one. And we have 8K, 8,000 images. The names are meaningless, but we can see the images here. So Let's start with the coding part. These folders, by the way, are here for the store the results we will see at the end of the coding session. But we can start with the basics of the Milvus. First, we need to import PyMilvus methods. We have connections here for the connect the Docker server, and we are using field schema for defining fields, data types, and collection schema. We are here collection schema. We are use that for defining the schema skeleton, and we need to obey the rules exactly when we create the schema with this method. Otherwise, we will get an error, and we have a collection method for connecting the collection in the Milvus database. First, we need, as I said, we need to connect the Milvus. Since we use Docker desktop, our host is localhost and port is this. We can use external resources as well, but for simplicity, we are using Docker. We are just using the connect method for connections library. Then we define our collection name. This need to be unique for the collection. We are accessing the collections with their names, and then we need to define the collections fields. Again, we need to define their names and the data types of the fields. For example, ID is an integer, and vector1 and vector2 is float vectors. These types are our vector embeddings. We will focus on these fields for vector searches. And again, we need to indicate a primary field, and these parameter is negligible, but we need to define a primary field too. This is a crucial part. We need to define our vectors dimension. These dimension varies depending on the embedding model. For example, we will use clip and dimension will be 512. But another model needs, for example, 1024 dimension. It changes, but it's important because if you use 512 dimension for a field, you have to give 500. You have to give the vectors in the dimension of 512 again. Otherwise, they will not be compatible, and you will get an error. Then we are creating our schema with the fields, and these parameter indicates that if a field comes when inserting, and if you don't have that field, it's creates automatically, but we do not want that. If you see the documents, you can see all the details. There are a lot of parameters, but we are just showing you the basics here. And as third, we connecting our collection. If we have the collection with the name training collection, for example, we will just connect that. But if you don't have the training collection, it will be created with the specified schema, and we use the parameter collection for further accesses. After that, we need to create indexes for the fields for faster and better access while searching. We are separating them as clusters, and of course there are a lot of ways, but we are using scalar index parameters as inverted and vector index parameters as inverted flat. Again, in documents there are a lot of index types, but here we are using these, and each index types has its own parameters. As in here, we have analyst for IBF flat. These index parameters help us to access fast and search fast, so it's crucial. You should do that. you cannot do the scalar index parameters, but you have to do vector index parameter for more efficient searching. After creating the parameters, we connect these parameters to the fields with create index method. We give the field's name and the parameters. After the construction is finished, we are ready to insert for data, but for simplicity, we are sending random garbage values. 1000, we will send two types of vector 1000 times, and they will be totally random because they will not have a meaning. But I just want you to see that we can how we insert. We will do the meaningful things afterwards. Here we are in a loop for 1000, and we create randomly two vectors. We create the entity with the vector field's name. After that, we can append these list, and we will just do we will just call the insert method. It's internally in Milvus automatically will batchify these and insert these as batches. In this way, it will be the optimum way to insert. So I recommend you to send it as a list instead of in a for loop. In each for loop, do not type collection insert data. Make them as a list and then insert them as a single line. Milvus will internally send this data list efficiently. We can run this script, and then we will search. First, we need to set up. Here, since we sent 1000 vectors with dimension of 5, it's fast. We inserted these, and now we will search the inserted vectors. This print result function just for beautiful printing. Details are here. It's out of our scope. It's just for beautiful printing. Then again, we need to connect the server, Docker server. Then again, we need to specify the collection name. And as I said, since it's created, we will just connect the collection with specifying its name. Afterwards, we will give the query vectors. Again, these are totally random. And we will indicate the search parameters. It's the new thing. Again, we need to specify the metric type, and it has to be the same with the indexes metric type. Here we created the indexes with cosine similarities metrics. And here we have to use, again, cosine similarity metric for searching. And its mprop is again search specific parameter for index IVF flat. For different indexes, we will need different parameters. But in our case, mprop is enough, and it's basically, as I said, we separate the data as clusters, and prop is the grouping the clusters. We look for the clusters 8 by 8. Then we load the collection to the memory for efficiency. Then we can make the search. We give the vector as data, again as a list. Then we specify the fields. Here we specify the field where we searching on. For example, if we give an image embedding, but we want to search on text, here we will type text. In the example, there's a usage of this. I will show that. Then again, we specify the search parameters. Then we specify the output fields that we want to see in the results. we can here, if you want to see ID, we can type here ID too, but it's not needed. And here we are specifying here their limit. With this limit, we will see just 3 results. If we do not specify, I think it's defaulted by 3, but if you type 5, we will get 5 limits, 5 results. If we have, of course, if we do not have enough image, of course, we cannot see that. But if we have image, we will see the best 5 results. We are doing it for another field with another query vector. It's the same thing. Then we release the collection from the memory because we get the results here. We do not have these collection in the memory now. And we can see the results with beautiful printing. Afterwards, I want to tell the hybrid search too, because then I will show both the results. Then for this time, we will specify the data in the search parameters. Then we will specify the fields in search parameters as separate. For example, query vector 1, I want to search query vector 1 on vector 1 field, and I want to search query vector 2 on vector 2 field. Then I'm sending 2 separate requests. I store them, and we use a ranker. There are 2 types of rankers in Milvus, RRF ranker and weighted ranker. Weighted ranker is basically we are giving weights of the requests. We will use weighted ranker in the example. And RRF ranker is very basically make them same weighted, but does some complex things in it. As I said, if you're curious, you can see the details in documents. Then again, we load collection into memory, and we make the hybrid search with hybrid search method. We send the requests, re-ranker, again limit and output fields. Our result is here, and then again we print it here. I want to run the script too. As you can see here, for the vector 1, we have the similarities here. They are not meaningful, so I'm not focus a lot on these results. But as you can see, in hybrid search, the score is lower because they are not meaningful. Since they are not meaningful, they cannot be a suitable vector in our database. For meaningful test, I'm going to continue with the example. It's a huge file actually. So we have a lot of libraries to import. Of course, we need to import Torch. Since we will use the clip embedding, we need to import clip and NumPy. These are just for better coding. These are the Milvus specific libraries, and these are for the managing the data set and other things. First, we need to custom collect function for the data management. From the CSV, we will process the images. These are beyond our scope, but if you are curious, you can read the comments and play a little bit with these functions. Again, we have data classes for managing the batches more easier and more efficient. Again, I'm not going to focus a lot on these. Again, we have image dataset for better managing. And our core class is here. Mills model. In here, we will set the collection, create the collection, search, insert the data, search the data, make the hybrid searches. Everything will do will be here, Mills model class. We need to specify the host time port, collection name, batch size if you need, and image base path for showing the images, and fresh start parameter for starting a new collection. If you have, for example, collection 1, but you want to create collection 1 from scratch, you have to make this parameter true. It's default as true, by the way. Then we are again connecting the Milvus. I'm going past this fast because I talked about this. If you have GPU, we will connect here, the GPU here. I recommend using GPU. It's fasten the process a lot. Then we load the clip models and we initialize our collection. In this method, if you have the collection, we are just connecting them. And if the collection, we set the fresh start parameter, then we drop the collection. Dropping collection means deleting the collection, basically. We just type drop collection and we delete the collection totally. Then we define the fields. In our example, we have 5 fields: ID, file name, caption of the image, vector of these captions, and the vector of the image. As you can see, we have 512 dimension here since we use clip, and we need to obey the dimension rule, which means we need to give the queries in dimension 512. Then we create the schema and create the collection. And again, we create the index parameters for the vectors. As you can see here, we used another thing, HNSW, for our vectors in this case. And we created the indexes. Then for dataset insertion in a batch, we need a process batch method. In this method, we will take the data as batches, pre-processed data. Then we generate their embeddings. As you can see here, we have a batch as a parameter, and it has image and text inputs for the clip. It's ready for the clip embedding. And we encode them, and we get the vectors. After that, we return another batch data with the embedding fields. We will use process batch method in insert CSV dataset method. We load the CSV data here. We take the datas, all of the datas. Then we will load the dataset as using data loader. Then we process in batches. In each batch, we will generate the embeddings and we return the metadata. And in metadata, we create the entities and we insert the entities to the Milvus. I said insert these as lists, but inserting as 8,000 sized list of the 512 dimension vectors, it will not work. So we will split the 8,000 images as batches. We get the embeddings of these batches, and then we will insert as in batches. Again, Milvus will do more efficient inside of it, and we can make the batches bigger and or smaller with this specifying batch size in our class. Then after the finishing the insertion, we flush the collection. Afterwards, we are ready for the searching now. And these are the search methods. First, single vector search. As Ecem said, we are giving a single query, single image or text actually, and we construct the embeddings. Afterwards, we will search the result embedding on specified vector field. Again, we have search parameters here. Cosine similarity we will use again. And depending on the input type, we will take the embedding of the text or the image. Here, for example, we're opening the image and process the image for clip. Afterwards, we get the clip embedding of this input image. Then we will select the fields we will search on. If you want to use select on text, we will use caption vector. If you want to select on the image, we will use image vector. Then we make the searches here, and we format the result for better printing, and we release the collection. And we return the results. Afterwards, we have a hybrid search method. It's basically the same thing in the first training files. Again, we take the input, we open the image. We will, as Ecem said, we will use just the images for the input, but there's a lot of type of hybrid searches. We will give the image, open that image, preprocess, get the embedding data, and then create separate search parameters both on the image vector and caption vector, and send separate requests, re-rank them. By the way, we are taking these parameters W1 and W2 in our method parameters. It's defaulted as 0.43 and 0.57. Then we format the results for better printing and releasing and returning the results. And the last two methods for just getting the stats of the collection and closing the collection. Now you can run this search file. We will use this file as a library actually, because there is just class definition here. We will not make any call in this file, but in example search.py, we will use this file as a library, and we will use these classes in the example search.py. Again, we have a pretty print function here. You can see the details if you want. And now we are using our class. First, we create our collection. We specify the image base path. It's here actually, Flickr 8K images. We will select the images, load the images from here. We specified the batch size as 64, and we stated prestart as true. Since I want to see from scratch. Then we insert the CSV dataset, and we specify the CSV path. Again, it's in this Flickr 8K folder. We will insert these and with using the methods I talked about. Then we will make the single vector search and hybrid search, and we print the results. And then we close the collection. I added comments here as detailed as possible. If you want, you can read these comments. Of course, you can read these comments too. If you feel not efficient. You can see the documents again, but the basics are here. Now we can run the example search file. Now, first, it will look at if we have the CUDA device in initialization part. And if we have CUDA, it will say we are using CUDA. And then we will insert the CSV data set. As you can see, it says using device CUDA. I recommend you to use CUDA because it fastens the process a lot. If you use the CPU instead of a GPU, it will slow down, I don't know, maybe 10 times slower it will be. And here, in our CSV, we have 8,091 entries, and it will take a little bit time to load this. But since we're using CUDA, it will not be too long. You will see the progress soon. In this part, internally, we batchify the data, and then we process all of them. After processing, we will insert again the batches into the Milus database. As you can see here, we load the images here. When it's finished, our database is ready actually, and the search will be done. Now the searches are coming. Yeah, for example, single vector search is done, and first result is our query result. I want to store these files in single results. Then hybrid vector search is finished, and also I want to store the results in hybrid results. Now, our program is done, and we have the results. First, I want to show you the input image. As it's the same in the vector stage, I can show you here. Our input image is this, and our first single result is this again, with similarity of with the similarity of 99%. It's near the same thing, and we can see the caption here. The second result is with 78%, and it's this. And the third result is this. We can see the captions of these images, and we can see the similarities here. I don't know why there is two hybrid search printing. I don't know. But shrinking and enlarging it's complicates the terminal. But I can show you the result. First result is again the same, but if you run again, actually we can make the search again with the neglecting this part. Since we insert the data, we do not want to insert again. So I set fresh start as false, and I commented out the insertion part. And I want to comment out again the single vector search part too. I will just make the hybrid search again to show you the result. By the way, again, the first result is the same in hybrid too. And the second image is different from the second image of the single result. As you can see, this is the single result image, and this is the hybrid results image. By the way, hybrid's first one's similarity is 73%. It's not 99% because there is some information loss for searching image embeddings on text embeddings because they are not basically the same thing. One of them is image, one of them is text. We use just the image embedding on both text embeddings and image embeddings. We basically trying to say, take this image, understand it, and find a similar text, which is summarizes the given image. So our similarities are normally reduced, and other the following results are reduced more. It's 53%, but semantics of the result is not very different. Maybe it may be better too because we have stairs here as in inputs, but we do not have any stairs here. For the first third image, we have 52%, and the image is, its single result is here, and the hybrid result is here. Again, they are different. Single, hybrid. It has smaller similarity for score, but semantically, it's not so different. I don't know which one is better, but I can say both of them is false or both of them are true. So these are the single vector and hybrid vector search results. You can play with the parameters here. You can play with the weights here. If you change the weights, results will be changed. For example, if you give 5.5 and 0.5, again, let's run again. The results will change. And change will be similar to the single results because we will focus on more image, not text. And as you can see, similarities are changed too. And our hybrid search results now is same with the single results. If you want to try anything else, you can, of course, play with the parameters a lot. If you can try changing base size and see the changing speed of the insertion. These are enough, I think, for the showing example. And good luck for trying and learning the things with the vector databases and hybrid searches. Thank you. Thank you for listening.